Thanks. So I'll begin with a bit of introduction about myself. My name is Sam Zimmerman. I'm the CTO and co-founder of Freebird. We'll learn a little bit more about Freebird in a minute, but part of what motivates this talk is understanding ways in which deep learning can be extended into risk management contexts. So I've been working in risk management for about 6 years now. And as anyone who's lost money on a model that they can't interpret will understand, I think this talk really tries to capture the work we need to do yet to enable decision-making in financial contexts and risk management contexts using deep learning methods. So the first part of the talk will have a little bit of a salesy feel as I explain what Freebird is and what Freebird does, and the main data science problems we're trying to solve. The second part of the talk is going to describe the way in which a particular problem for a particular model that our team is leverage deep learning differentially compared to other methods to solve. The third part of the talk, which is the most kind of advanced and the most interesting research we're doing, is extending deep learning methods using Bayesian deep learning to interpret and understand those results a little bit better. So to start, I'll offer a short explainer video that explains the problems Freebird is trying to solve.
We've all been there. You're traveling somewhere important when your flight is canceled or significantly delayed. So what are your options? Wait in line to rebook? Spend time on hold with the call center? Shell out big bucks for a last-minute replacement ticket? You feel powerless and overwhelmed. Availability is disappearing by the second, and you've got somewhere to be. Freebird is here to help. Freebird is a simple tool that gives you rebooking control. When your flight is canceled or significantly delayed, Freebird empowers you to instantly book a new ticket on any airline at no additional cost. Purchase Freebird coverage through your travel agent or at getfreebird.com after you buy your flight ticket. If your flight is canceled or significantly delayed, Freebird will notify you immediately. From there, it's just 3 taps to rebook for free via your mobile device. Tap to open your alert. Tap to select a new flight. Then tap to confirm your selection. It's that fast and easy. With Freebird coverage, you're in control. Travel empowered with Freebird.
So, as I hope the video explained, you pay for access to Freebird before your trip. It varies, and we'll get into why and how that varies in a bit, but it's about $20 for each leg of your trip, so outbound and return. Now, as a startup, we've raised millions of dollars from top-tier investors, including General Catalyst and Accomplice, people who have built Airbnb, Kayak, and other major travel brands. And empowering all of this offering is our risk model. Our risk model is what we call a collection of models across our problem domain that produce estimates about the likelihood of a flight being disrupted, the likelihood of missing your connection, the likelihood of a cancellation occurring, or a storm shutting down an entire airport, as well as the expected cost to buy a new ticket. And as anyone knows, dynamic airline prices can be quite difficult to predict. And we're having to predict that in very low availability moments whenever everyone's scrambling to buy a new ticket. Now we think about this risk in terms of expected loss. So while we charge about $20 one way, a part of that risk is what we're going to have to pay out in buying new tickets. And each ticket and each trip has a variable likelihood of being disrupted, as well as a different cost to replace that ticket. So if you're flying from Boston to to Chicago, 2 very windy cities in America, the likelihood of your flight being disrupted is higher, as well as the cost to replace that ticket because it's a really busy commuter route. Whereas if you're flying from 2 very sunny locations, the likelihood of a flight being disrupted, as well as the expected cost to replace the ticket, may be lower. Now, the set of variables with which these 2 major key pieces of our risk model can vary are immense, and we've worked for over 3 years to understand and quantify the risks of offering our product. So that I hope you now kind of understand some of the core ideas and problems we're trying to solve at Freebird. Today, we're going to try to answer a slightly different problem, which is, of your flight departing today, what is the likelihood and magnitude of that delay? And so as a result, we needed to assemble a massive database. We have over 1 billion files spanning our entire problem domain. So we have data that one data feed that is a stream of all priced itineraries, all priced trips across the entire world. This data, we get about 5,000 different requests per minute for that feed. We also get about 200 megabytes of data a day on flight statuses. Our our servers are ingesting all flight statuses across the entire world, and at any moment can reconstruct the state of the airspace to understand the ways in which a flight getting stuck in one city or a plane getting stuck in one city might cause a delay in a flight much further away. Now, the important thing to understand about this problem, what makes it incredibly difficult, is that at the time we're having to make our prediction about the likelihood and severity of a delay, we have differential access to data. So if we're making an estimate, 30 days out, we might only really have climatological information, seasonal information about large-scale trends. But as we get closer and closer to the time of departure, we get access to much more information. The day of departure, we're able to ask things like, where was the plane before, or where was the plane coming from, and where was it coming from before that, as well as understanding how major weather systems are impacting the U.S. airspace. Because of the network effects in the U.S. airspace, a hub like a major city like Chicago going down can impact the entire rest of the U.S. airspace in ways that are really hard to understand. And we've spent a lot of time using network analysis to try to better quantify the impacts of those larger nodes on smaller nodes. So we're a really small startup. We don't use deep learning just to use deep learning. We first tried a number of a lot simpler methods to estimate the likelihood of a delay 24 hours before departure. And what we found is that a lot of traditional, very industrial-friendly algorithms like random forests and linear regression simply weren't performing as well as an RNN. And I would say that in this model, this estimate is actually one component of our flight-by-flight prediction model, but even the RNN is not quite at the level where we can expose to end travelers. This model actually is, as a result of kind of the performance at this point, is only exposed to our internal agents, so we're helping people rebook during these times of disruption. Now, the why I think that deep learning did differentially outperform, I think the first thing is that we, as the earlier speaker alluded to, we actually have a massive amount of data, and so a lot of methods were not scaling in a way that was super friendly to the feature space that we are trying to understand. The second point, which I think I alluded to a bit earlier, is that the feature space is large, and there's a lot of nonlinear interactions between things like weather, origin weather, inbound flight delays, as well as the way a certain carrier chooses to economically run its flights. So there were a couple challenges in this approach. I think machine learning and deep learning in particular are really robustly developed in one domain, vision, and I think they're also a lot better in other domains like sound and language. Our problem domain is such that we have a lot of categorical features as well as continuous features. So we needed to have a normalization step beforehand to embed our categorical information into a representation that was much more friendly to deep learning techniques. this map here is a map of it's a representation using PCA of the nearness of different delay patterns by airport. And for those of you who have flown through America, there's kind of some intuitive results embedded in there. For example, the entire New York corridor kind of tends to go down and function well in one step, even though it's 3 distinct airports. So this is kind of the basic architecture that we used, and the chart on your left is our performance, the observed delay versus the predicted delay, with an OK correlation. This is actually kind of an earlier model, and I'll talk about our newer model in a bit. Now, I hope by this point to have explained why data science and statistics are important to Freebird. And I hope to kind of have motivated some of the core problems we have, which are trying to understand and quantify the risks of taking a trip. At the last part, I kind of showed you a model where deep learning differentially outperformed other methods. But as combining those two ideas together, the question is, how can we, if we have a prediction that's really quite accurate, how can we start to understand the uncertainty around that estimate in a more holistic manner? So most of the models that we build are from a kind of a different branch of statistics than a lot of AI and ML methods, and that's Bayesian statistics. Bayesian statistics is a type of is a way of building a model of the world using probability distributions that work well together, and then adding data to then produce better distributions that you then sample from for your predictions. Now, there's a couple of major advantages to having a model of the world. One, which is quite important to risk management, is that you can understand what aspects of the problem you understand well and what aspects of the problem you don't understand well. Deep learning methods and a lot of other machine learning methods don't allow you to really robustly understand what aspects of the problem or what features are contributing to your inaccuracy or accuracy. Now, the major issue with Bayesian methods is that they tend to be very computationally expensive. When you're trying to combine that data and those probability distributions, that you end up having to integrate over kind of an output distribution called a posterior distribution. And when you're performing that integration, it tends to be computationally intractable. And so that's one of the major reasons why you don't hear about Bayesian statistics as much, is because while it's quite robust and well understood, you're not able to kind of scale it to the big data problems that many modern machine learning problems have. So that kind of provides a little background about Bayesian statistics. Now, deep learning, while is differentially outperforming most other methods in most other problem domains, is actually only producing point-wise estimates. So it's not out of the box giving you any sort of understanding of what the possible outcomes could be for that estimate. Or even in a more basic sense, how confident the model is about a given estimate. And so the Bayesian deep learning is an attempt to interpret and leverage some of the skills that Bayesian statistics have in a deep learning context. Now, I'll provide a bit more context as to why and what the way we tie these two things together. So, as I mentioned earlier, Bayesian statistics has a very expensive integration step. And there's a couple distributions that are more friendly to distributing that calculation across many different servers. And so in the early 2000s, I think perhaps late 1990s, variational inference is a manner of taking distributions that are very computationally expensive to produce and approximating them using distributions that are a lot more computationally friendly and easy to distribute, enabling you to approximate Bayesian behavior while not having to complete that really expensive, potentially intractable integration. And so Bayesian deep learning, to tie this all together, is a way of interpreting or understanding a deep learning technique called dropout. Dropout is, sorry, this is getting quite involved, several steps down. Dropout is a technique that's made deep learning very, very high performing. And in dropout, what you're doing is you have a complete network, and you're arbitrarily dropping out certain nodes. And by doing so, you're actually able to produce better generalizations to new problem domains. And it's one of the main drivers of deep learning success in the past 5 to 10 years. Now, dropout can be understood, and what kind of the field of study that we're really interested in and focused on at Freebird is understanding and interpreting dropout as a type of variational inference, as a way of approximating these different smaller distributions. Now, this work was championed in the 1990s by McKay and has recently been popularized by Yaron Gao. And I think that the New Yorker cartoon to the side captures the importance of really the work we're trying to do in understanding and interpreting what these models are doing. So, that work. So, there's a couple major advantages to Bayesian deep learning. The first, as I mentioned, is that it's scalable. You're able to leverage the cheapness of modern compute in a manner that allows the problem to be cut up into smaller pieces and solved rather quickly. The second thing is that it does allow, as you see kind of on the image to your left, a type of uncertainty estimate. And so while there's a lot more you'd want to know, there's a lot richer understanding of a model that full Bayesian statistics give you, having uncertainty bounds is a step in that direction, and it's the most promising method so far of doing so. And I think the third point, which is one that's kind of somewhat counterintuitive, is that one of the advantages of Bayesian statistics is that you can understand which parts of your data set are more important to your model and then weight them intelligently. And so I think that another advantage of these Bayesian deep learning techniques is that you can understand and also differentially give more data to your model that is relevant to helping it understand the problem. So, the model, to kind of bring it back to Freebird's case, the model here, we're trying to predict the likelihood and severity of a delay 24 hours before departure up and until the time of departure. And the use case for us in a future world that we're still not quite there yet is enabling travelers to rebook preemptively. So before your flight's canceled, before you miss your connection, sending you a text and saying, hey, this flight's, it's not going to go very well. Why don't you rebook for free? Taking all the stress and strain out of your trip, not even having to be scared that your flight's canceled. And so far, our initial results suggest that across all major airports, as well as some smaller airports, we're able to understand both the likelihood and the severity of the delay in a well-calibrated manner. Now this plot, which I think looks rather simple, but is quite important to the work that we're doing, is an uncertainty quantification plot. And so starting with the plot to your right, you want to ask, when a model says, I'm 50% certain about this estimate, is it actually well calibrated? 50% of the time is it right, 50% of the time is it wrong? And so a perfect model would be totally, would be that orange dotted line. The results of our model and analysis are actually that blue line, which suggests we're quite well calibrated. Now you might ask, well, in aggregate, is that the case? But is that potentially weighted by several larger airports? What we actually find that is across many different airports, we actually see a similar well-calibrated estimate. So our model, when it's making a prediction, is able to say with some confidence how likely it is to be correct. an interesting aside here, which I think was counterintuitive to our folks, and we double checked it a couple times, is that the impact of weather steps ahead, where steps ahead is a feature of an RNN where you're plugging a prediction for the likelihood of a delay 2 hours out into your model that's producing an estimate 3 hours out. We're actually seeing a fixed cost in our prediction estimates, which is quite surprising. I think it's also quite intuitive that weather does have a major impact on predicting these flight delays. So I think I'd like to close with 3 takeaways. The first is that in our particular problem of estimating the likelihood and severity of a flight being disrupted, deep learning is differentially outperforming other methods. The model I walked through today is our airport estimate, which is a component of that prediction. 2 is that risk management applications, domains where you have to understand you don't only want to make a good prediction, but you also want to understand the other possible outcomes if your prediction is wrong, require a lot richer understanding, a lot more built-up model than what current deep learning methods give you. And the third is that Freebird has performed work to extend these deep learning to enable uncertainty quantification estimates to be extracted from our models. I'd like to end with a bit about our team. As I mentioned, this is our only deep learning model we use. The rest of it is Bayesian statistics. And this is a simple GIF of an MCMC sampler learning Freebird's logo in real time. So if you're interested in Bayesian statistics or the intersection of Bayesian statistics and machine learning, please talk to me after the conference. While I am the CTO and co-founder, much of this work was done by this team, particularly TJ Vandal, Max Livingston, and Cayman Piho in this particular talk. I'd also like to flag that PAPI's has been an exceptional conference for us. We actually submitted this work to PMLR through this conference, and it was accepted. So we're both thrilled and excited to contribute to pushing the boundaries, and thankful to this conference for giving us the ability to make it happen.
Thank you, Sam. Any questions for Sam?
Hi, very good talk. My question is about did you guys compare 2 questions? Did you guys compare the normal Bayesian statistics that you can run offline with your neural networks using Bayesian to give you more like a white box approach in a matter of prediction, Bayesian is 20 times lower, but is 1% better or something like that?
We did, but we kind of tripped at the first step. Bayesian methods weren't scaling even close to our problem domain, so we didn't. We tried it with much simpler, smaller problems, and in our traditional risk management problems, we're constantly fighting with scaling our samplers. It simply wouldn't have been. We wouldn't have been able to get comparable performance. Okay. We wouldn't have been able to evaluate the models, given the difficulty of setting up the inference.
Okay, thanks. So the second question, and the second question is, you mentioned that you use, I think, logistic regression and random forest, and then you compare them to LSTM on the matter of the, I guess, the forward pass. The running time of the forward pass was on one of your main focus,
yep.
I guess. But as you said, there are a lot of categorical features and and continuous features. But if you're using LSTMs, you are first interested in the time correlation of the features, right?
Yep.
And in the talk, I couldn't see if you guys are doing time series that normally interval samples, or is like a point process, like event 10 days from today and 5 days and 2 days. And if it is, the answer yes, it's point process, how do you guys tokenize the timestamps of the data? Like if the data passed 5 days before and 2 days, how this token is different from 10 days to 2 days? I don't know if you understand.
Got it. So in our framework, we're only doing the previous step. So we're not having to worry about kind of indexing those previous timestamps. So I guess that answers both of your questions.
Okay. Thanks. Thanks a lot.
Hi, I have one question and one curiosity. You said that you have the data if the company, if that plane will go to another destination, just stop and get more. So how do you get this information? Because the flight status, I think that's public, but the other information that could be from the companies, how do you have access to this kind of information?
The short answer is I spent 3 years of my life scouring the globe for access to these data and data sets, in particular in the flight status domain. We actually were the first people to kind of come with a really sophisticated statistical interest in the data, and actually we actually had to pay them to extract new data that they didn't think anyone wanted.
So it's not public, you need to pay the companies to get access to this data.
Yes.
Okay. And the second question, you said that you were using network analysis because of the hubs like Chicago. So how do you incorporate this information in your model, or how do you use this information?
So we particularly have been focusing on that in episodic risk. So when we think about risk at Freebird, we think about 3 different types of risk. We think about risk like if you're driving a car, there's a lot of fender benders that happen, and we have models that estimate fender bender risk. There's also catastrophe models. There's terrorist attacks. There's really massive events that have a large amount of impact on our risk. Those are catastrophic risks. In the particular problem domain where we spent the most time in understanding network analysis is episodic risk. So that's something like a major hurricane or thunderstorm coming through and knocking out part of the network. And the questions we're trying to understand are, when this node goes down, what are the other nodes that are impacted? And what is the resiliency of the network? What's the ability of the network to distribute the load across other key nodes? And so we're other major nodes. So we're focused on that network analysis in that episodic risk where it's only taking down part of the network. I encourage you to check out resilience studies, networks of resilience studies, which I think have some of the most advanced approaches to understanding the robustness of networks to perturbations.
Well, thank you for the very interesting talk. You said that you currently are publishing results that you obtained on a new type of technique for Bayesian LSTMs. Mm-hmm. My question is, I've been struggling in the past to actually do research or lead my teams to do actual research on those kinds of advanced topics. It seems that the short-term needs of the product always kind of ends up trumping your ability to actually write a paper and publish and test this new state-of-the-art research. And how do you guys balance it?
Yeah, totally. So I would say there's kind of 2 drivers there. The first is that as a startup with a lot of IP in our core risk models, so our models that we use to price our product, we can't just show investors that. We can't show the public that. But we need a way to demonstrate expertise. We need a way to show that we are capable and understand statistics. This, by publishing, we're able to provide an external indication about our ability without having to show all of our internal models. The second answer, which I think is an important thing to understand in a startup context, is that your people are what matter the most, and data scientists who are exposed to lots of methods, particularly more difficult methods, are both happier and are going to be able to perform better at their day-to-day tasks from their work in harder problems. And so I think the first is understanding, having a holistic approach to building a team, as well as kind of understanding that there's a need to communicate expertise.
That's going to be the last question. All right.
So just stepping back a bit, so you talked about that you use linear regression and random forest. So is your data relational or it's not?
Is our data relational?
Yeah.
So we have a domain model. The feature creation process is such that we don't have a domain model for all of our features. The vast majority we do, but it is not relational. We're mostly, we actually kind of have done a lot of work in the MapReduce and Hadoop-based space, and so it's not in a format that is relational whenever we're training.
I see. Thanks.
Okay, as Sam was saying, there's a paper. It's going to be published soon. We're still finalizing a few things. So it's published via the proceedings of PEPIS, the previous conference we had in Boston. Sam was one of our speakers in Boston. We're hoping to also bring some of our local speakers here in Brazil to the Boston conference. Looking forward to reading more in the paper. Thank you very much, Sam, for the kind words about PEPIS. Thank you for the paper that you submitted. And please, another round of applause for Sam.